Okay, welcome ladies and gentlemen to the beginning of our next set of lessons. Now it's not really a full chapter to start off with, but we're going to start off with 8.1 and 8.2, and then we're going to head back to chapter 7. I feel that 8.1 and 8.2 connect really well to chapter 6, and then we'll move back to chapter 7 and finish up the trig, the little trig thing, or the big trig things. Okay, so 8.1, this is the first of two videos. This is the easier of the two videos. This is the law of sines. So all of the trigonometry that we've been doing so far has dealt with right triangles. The law of sines is a way for us to get out of right triangles and into more real-world applications. The right triangles don't always occur in the real world. Sometimes, I mean, most of the times, it's not going to happen in real world. Like, we've done problems where we've had to measure the height of a tree. Well, let's say that tree is not actually standing at a 90-degree angle. But there are still ways that we can solve those particular problems using law of sines and the law of cosines. The law of cosines being from section 8.2. So let's go ahead and take a look at what this is. So there is a proof for this, but I'm going to omit that just for ease of use. This is going to be a useful piece of information. The law of sines is actually a very easy one to memorize. And what it says is the ratio of the sine of an angle to the length of the opposite side is the same for all three angles of any triangle. So if we think about what that means before I just write down the equations, if I think about it, if I have some random triangle here, it's not a right triangle anymore, and if we label our our angles, big A, big B, and big C, you do need to know that our little a goes across from big A, little c goes across from big C, and little b goes across from big B. What this is basically saying is, first of all, the ratio of, well, ratio just means fraction. The ratio of the sine of an angle. So the sine of some angle, let's call it A. So the ratio of the sine of an angle to the length of the opposite side, oh, that's little a, is equal or is the same for all three angles. So we have sine of B and little b and sine of C and little c. And that actually is our formula. So we have, don't worry about the word or there. So we have the sine of A over A is equal to the sine of B over B and the sine of C over C. And if you need a triangle to help you kind of see this, again, just draw down this triangle here. I know I put the things in the different spots, but it doesn't really matter where you put things, as long as the side goes opposite the angle. And this is actually really kind of simple, really kind of cool, that now with this simple formula, simple equation, we can solve triangles that would exist in the real world more than just the right triangles themselves. Now, there is a second version of this, so pay close attention here. That's all we're going to do for a second version. The first version being this that I have up there right now, the sine over the A. This is usually pretty helpful if you're solving for an angle. It just makes the math a little bit more simple if you're solving for an angle here. Or in the second version, it's a little bit more helpful if you're solving for a side length. But it all depends on the problem that you're dealing with. Now, there are only certain kinds of triangles that this law will work with. So you have to look at this and go, okay, well, in an equation, I only need one equal sign, so I don't really need this statement right here. In an equation, this equation that I have left, I have A, B, and B. Well, that's 4 variables. in order to solve anything, I need to know 3 of them. So I could know big A, big B, and little b. So if I knew big A, big B, and little b, let's see what that would look like. Big A, big B, and little b. So that would look like this. If I knew this information, I could solve for, let's use a different color here, I could solve for little a. Well, that's interesting. Okay, if I knew from this statement again, if I knew, well, I could say I could know little a. So if I knew little a, that would help me solve for little b. And likewise, we could do this any way here. We could say, oh, what if I didn't know big A? If I didn't know big A, I would need little a and little b so I could solve for big A. Now, you might be thinking of, you have seen something like this before back in geometry, and that's true. If we went back to the very first version there that we had, and we said I knew little b and big A, well, if you look at this, I have an angle, and a side. Oh, that's cool. That kind of sounds like a little bit of geometry, angle, side. And that is kind of how we look at this. If you're given 2 angles and the non-included side, you could solve this particular triangle. Also, if you're given angle, side, angle, so if you're given 2 angles and any side, you can use the law of triangles. So I'm going to mention that here. This is 2 angles and any side. And the third way that we can use law of sines is for the SSA. Now you might remember from geometry that that was kind of a special thing that you weren't allowed to do. But in the law of sines, it actually does work sometimes. This is the special case. We call it the ambiguous case because it doesn't always tell us right away what's going on. Sometimes it creates 0 triangles, 1 triangle, or 2 triangles, and that's kind of obnoxious. But that's going to be the second part of the video coming up later. Right now, we're just going to be dealing with the AAS and the ASA versions and solving the triangle. Now, you do have to remember that when you solve a triangle, you are looking for all of these things in red. So you are going to have to solve for 3 different pieces. Also, one thing that I'm going to mention that you might want to write down, you are not allowed to use Pythagorean theorem. Pythagorean theorem only works for right triangles. None of these problems are going to be right triangles anymore. All right, so let's take a look at a problem like this. So you're given a triangle. It's triangle ABC. I don't care how you draw it. Let's say A is 36 degrees because that's what it says. So here's angle A. That means little a is across from this. And it tells me B is 48 degrees. So now our goal is to figure out what is big C, what is little c, and what is little b. So let's do some math. This is the AAS version. So this is an AAS triangle, which means law of sines is legal. And what this tells me is, well, first of all, I'm looking for a side first, little b. Not that that's exactly what needs to be done first, but that's what I want to do first. If I'm solving for little b, I know that little b goes over the sine of b, so 48, and that's going to equal the 8 for little a over the sine of big A. Now here's why this is actually a very simple process. Solving for b just says multiply both sides by sine of 48. So I get b is equal to 8 times the sine of 48 all over the sine of 36, which is approximately, if you do this on your calculator, in degree mode, make sure you're in degree mode. I go 8 sine of 48 divided by sine of 36, and you can do it all at once. I get approximately 10.11. So that means B is 10.11. And what you should probably do off the side of your paper is you go, okay, big A, big B, big C. I know A is 36. I know B is 48. You could probably figure out what C is pretty quickly. And then I know little a is 8. Now I know little b is 10.11. So now the only thing left is finding big C and little c. Well, big C is really easy because we should know that the angle sum of any triangle is 180 degrees. So big C is equal to 180 minus 48 minus 36, which is 96 degrees. And that's actually okay. Remember, we're dealing with non-right triangles. And then we need to figure out little c. So now we just use the law of sines again. Again, we cannot use Pythagorean theorem. Now here's where things are going to be really up to you, but not really up to you. Do not use the 10.11 as part of your next calculation. Because 10.11 is rounded, your answer for C will be incorrect. So what we want to do is we want to say little c over the sine of 96 is equal to 8 over the sine of 36. Multiply by sine of 96 tells me that little c is 8 times the sine of 96 divided by the sine of 36. And that is, really quick, 13.54. So I come up here and I fill in my last little box. And I go, hey, I've solved this triangle because I know all 6 parts to my triangle now. Okay, so again, the ASA and the AAS versions are going to be very simple. That's all I'm assigning on this first half of the lesson. I'm not done. Don't stop the video. Okay? Because you're probably going, Mister, this is too easy. There's got to be something else going on here. And you're right, there is. There's word problems. Okay, this particular word problem is rather challenging. And I like throwing the challenging problems on here. So what I want you to do is kind of pause the video, read this word problem, and see if you can come up with the picture that's involved. Now, the picture is the hard part to draw. But it's a good picture to be able to draw. Okay, so let's see about this. All right, hopefully you've tried to draw the picture. I'm going to try to draw the picture as well. So here's flat ground. And I know the road slopes at 10 degrees above the horizontal. So here is my road. and I know it goes up at 10 degrees. Then you have a vertical telephone pole. The telephone is a vertical pole. Some people don't actually know what vertical means because they look out at the Kaumanu Avenue and they say, hey, is this vertical? Because it's vertical on the road itself. But then I ask them, what does a pole look like on a hill itself? And the pole actually looks like this. It's straight up and down. Okay, then you have the rays of the sun. The sun comes down from above, and it's going to come down the hill, and it's going to create this shadow. Now, the thing is, people are a little bit confused now as to what the heck is going on. And that's usually the case. Okay. Let's say the shadow hits right there. Now, here's the problem with this problem. It says the angle of elevation to the sun is 62 degrees, and the pole casts a 14.5-foot shadow. Okay, well, that's nice because this is right here, the shadow, which is 14.5, oops, not degrees, feet. And the question is, where's all my other numbers? Because I can't solve this triangle without numbers here. Well, here's where you got to do a little bit of thinking. Darn, right? So the sun has an angle of elevation of 62 degrees. And if it's an angle of elevation of 62, means it was actually an angle of depression if you wanted to come up here. The depression was 28. Oops, got to change that. Sorry. Was not paying attention to my own stuff as I was working. Okay, let's get rid of those dashes there. Okay, let's rephrase. The angle of elevation is right here. It's going from this line up this direction. Well, if we continued this over this way, this would create a right triangle right here, which would mean that this is my 28-degree angle. All right. And the rest of the math is actually not hard. If the angle between this line and this line, the black line here, is 10 degrees, that means the angle inside the triangle is 58 degrees. So now we actually have a triangle with enough information. We have an angle here of 58. Sorry, not 58. Gosh darn it. 62 minus 10 is not 58. Hi, Chihuahua. Okay, 52. 52. This is 28. And this is 14.5. And look at that. We have angle, angle, side, which means technically we have enough information to solve for the height of the pole. So we get x over the sine of 52 equals 14.5 over the sine of 28. I forget what it is off the top of my head. .33. So that means the pole is 24.34 feet high or tall. Now, honestly, the math wasn't hard. The writing the picture was the hard part. They're probably not all going to be this challenging. So I really do want you guys to try to draw the pictures if they don't give you a picture already. Now this particular textbook likes to draw the pictures for you, which is good and bad at the same time. All right, one little thing left to fill out here is the area of an oblique triangle. So if you're not given a right triangle, you can actually find the area pretty simply. The area of any triangle is 1/2 times the product of the lengths of two sides times the sine of their included angle. So given some triangle over here, A, B, C with little a, little b, and little c, if you were to take the sine of A times the sides beside it, divide by 2. So it's 1/2 times B times C times the sine of A will get you the area of an oblique triangle. And you can use any one of these three, depending on what you're given. All right, very simple formula for you guys to follow. Very cool, though, because now you don't have to think too hard about how to find the area of a triangle. Here's the assignment. I'll have you guys, or hopefully I'll have you guys an assignment sheet tomorrow morning. I will see you guys tomorrow.